Sounds good. All right, so last time we started talking more about directed graphs, and we focused on this problem of connectivity. Can point A get to point B at all? We weren't worried about, for example, how long it took to get from point A to point B. We started with DAGs, which turned out to have a very strong order based on who can reach who. This is related to this notion of topological orderings and topological sorts. Then for directed graphs in general, we started talking about depth-first search and analyzing that, using that to figure out which vertices a vertex V can reach. And then that sort of culminated in this discussion of strongly connected components. These are the kind of pairs of vertices that can mutually reach one another. And it turns out there's kind of a lot going on there. For one, if you contract the strongly connected components, what's left is sort of a DAG of these contracted vertices. And it turns out that if you're very clever, you can actually extract all of the strongly connected components in linear time with like a few different applications, ultimately, of depth-first search. Okay, I think it's almost the most impressive thing I can think of that we can do in linear time. It's faster than sorting. Okay. All right, so today we'll keep focusing on directed graphs, and the primary topic of today's discussion is what's called the longest path problem. Okay, so just to be explicit, by path I specifically mean a vertex cannot repeat. A walk is just a generic kind of going from point A to point B. When I say path, I specifically mean like a simple path where none of the vertices repeat. Okay, so a simple question one might ask is, you're given some graph G, and what is the length of the longest path in the graph? Say in number of edges, that's also roughly the number of vertices, since it's a path, vertices can't repeat. Okay. A special case of this problem is finding a path that can visit all the vertices. So every vertex gets visited exactly once. That's called a Hamiltonian path. Okay. All right, so I don't know the answer to this. I guess in this graph on the right, what is the longest path? I'll give a little time to stare at it. Okay, maybe I'll just ask, I'll start small. Did anyone find a path of length 3? Okay, how about 4? Okay, most people did 4. 5? 6? A couple hands remain. 7? 1, 7? Is 8 possible? No one found 8? I don't know the answer. Do you feel like you have? Oh, okay. All right. So we have an 8. Okay. Can anyone get 9? Okay. How high can you go? Can you get 10?
I don't think so.
All right. 9 is apparently the best one. Let's see if that there does exist a 9. Tell me what your length 9 path looks like. Where should I start?
So you see the farthest right node?
Here?
Just to the left of that.
Here.
Yes.
Okay, I'll start here.
So then you go diagonal down and to the left.
Okay.
Diagonal up and to the right. Up and to the left. Then straight up. then to the left, then down, then like slightly up and to the right,
We're doing pretty well.
down and to the right, up and to the right, and then down.
All right, how do we do? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I miscount? Okay, 1 second. 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10. Okay, you got 10, if I counted correctly. Okay, so that's pretty good. That was better than I expected. I had no idea. And again, this is a relatively small graph as far as real problems go, and I think it was at least tricky. It's not obvious. It's still not obvious, 100% obvious, that this is the longest one. I'm just matter-of-factly impressed by length 10. Okay. All right, so that's the basic style of question here. Okay, and we're going to discuss the problem in two settings. One is the case where there's no cycles in the graph. That's a little bit simpler. And then we'll look at the general case where there are cycles and so on and so forth. We just did the general case together. Okay. So I've set up a vote, as usual. And as usual, who's not going to vote? Oh, more than last time, okay. All right, about 6 people. All right, so for DAGs, it can turn out to be as hard as that, or there can be a polynomial time algorithm. We call that easy. And then same as general, hard or easy. All right, so who thinks that it'll be hard in DAGs? Okay, I'll put that like 10%. Who thinks it'll end up being easy? Okay, I'll put that at like 88%. All right, now general graphs. Who thinks it'll be hard? Okay, I'll put that like 77%. And then who thinks it'll be easy? Okay, like 1%. Okay. Okay, sounds good. At least it makes sense that on the whole we think that DAG should be easier, if anything, than the general graphs. That makes sense. Okay. All right, so we'll do DAGs first because it's a little simpler. So again, here then is a picture of a DAG. If I asked you what is the length of the longest path in this one? Well, granted, it's a little bit smaller, but I think it might be easier to find the answer as well. Does anyone see one of length 3? Okay. And then what about 4? And what about 5? Oh, did I miss one? Okay, 5. 6. Okay. 7. Okay, how did you get 6? Yeah.
Starting at the top left.
Oh, maybe you can't get 6. Okay, starting here.
And then diagonal down to the right.
Okay.
And then up to the right. Up and then
That is 6. Okay. All right. The best I had was 4, which is pathetic. Okay. All right, so this is 6. Okay. One thing kind of nice about this is that the way we've at least drawn the DAG, you can always do this with the DAG. I've drawn the arrows going from left to right. So at least you can kind of make some progress. Okay. Now, one thing very nice about DAGs, though, one sort of requirement of the problem is that it has to be a path, right? Vertices aren't allowed to repeat. But if there's no cycles, vertices can't repeat. Any walk is a path. Okay? If I'm walking around and I have repeated vertices, that's a cycle. Somewhere there was a cycle. Okay? So, as far as this problem is concerned, it's the same as also finding the longest walk, say measured in terms of the number of edges we use in the DAG. Okay. All right, so, right, so with that established, then my question is, does anyone have any ideas for approaching this problem algorithmically? Yeah.
Since you have to check every path pretty much anyway, the brute force would be doing like a breadth first search and just checking every path, and whichever results in the longest is the longest path.
Okay, so let me mention two words that were mentioned there. One is sort of simultaneously you said check every path, in some sense, or brute force was another word that kind of came up, and the other suggestion was breadth first search, which is among the topics for next lecture. Okay, so what does breadth first search do, right? You start from some vertex, and you kind of find the vertices that are 1 hop away, the vertices that are 2 hops away, vertices that are 1 hop away, vertices that are 2 hops away, vertices that are 3 hops away, and so forth. Okay, we'll discuss this next time, but this is actually going to find you very short paths to get from point A to point B. For example, if I ran breadth first search from the starting vertex of what we think is the answer, okay, it'll say, oh, these vertices are 1 hop away, and these vertices are 2 hops away, and these vertices are 3 hops away. In fact, it won't find our solution that we know. So breadth first search is good at something else, and we'll discuss that in greater detail next time. And in particular, it's not actually checking every path. It's actually much more clever. It's finding certain shortcuts. Okay. All right, so it won't be breadth first search, but we can try to do something like check every path. Of course, naively checking every path is going to be bad. Yeah.
So I think you could do something like that, but you basically save like subpaths and note like which ones have specific lengths, and then you can kind of like for each like subproblem add on the subpath length and just like take the longest of all those, I guess.
Good. So we can try to check every path recursively. But why, though, in particular, is that a good idea for DAGs? And why do DAGs play nice with recursion? Yeah.
Oh, I was just going to say because you're doing a lot of like repetition of subpaths.
Yeah, you're doing some repetitions, and yeah?
Okay, so I was thinking that like since it's a DAG, you could put it in topological order, which would make like there be an order to like when you're recursively calling on something's next or some other vertices, right?
Yes, perfect. So we're going to do recursion, and now I want to point out this is also kind of came up implicitly last class, why recursion is great with DAGs. When we do recursions, the first thing to worry about is infinite loops, right? But for many of these DAG problems, an infinite loop will kind of map to a cycle in the underlying graph, as we'll see. But there's no cycles in a graph, and consequently things become much nicer. This is also made explicit by the topological ordering, where all the edges go in one direction. Okay, so let's do that. What do I have here? Okay, so I have set up the recursive spec for us already. And at some level, we're going to fill in what was suggested. So I'm calling LW of a vertex V to be the length of the longest path starting at a vertex V. So LW for longest walk. Now that we know longest path and longest walk are the same thing. Okay. And if V is a sink, if there's no vertices, no outgoing edges, then the answer is just 0, right? The walk cannot continue. So for us, this was a sink. If I'm at that vertex, there's nothing to do. Okay, so that's my base case. That I've also filled in. So now I've left as blank what to do in the general case for a vertex V that does have outgoing edges. I'll leave maybe 30 seconds more just to think about it, and then I'll call on the first hand. Okay, maybe people have solved it, but yeah. What are some ideas for plugging in this inductive step? Sure.
Longest walk of all of its children without marking if they can see or not.
Sure. Okay, so first by children, I'm assuming you mean if this was the vertex in question, everybody with an outgoing edge? I mean, every out neighbor, sometimes it's called. So, okay, so you said longest walk, did you say the maximum over all of them or something?
Yes.
Okay, so I'll take the max over all the edges that are leaving V. So here's some notation. Sometimes this is called like the out cut of V. It's kind of, anyway. These are all the edges leaving V. Okay. L, W of W. So here I'm looping over all the children, as you said. And I'm getting the longest walk. Is that what you have in mind? Okay. Yeah.
What's the symbol V comma W is an edge in what?
Yeah. So I wrote, this is some notation for what's sometimes called the outcut of V. We'll talk about cuts more later. But this is just the all edges leaving V. Okay. If it was a minus sign, that would denote all the edges going into V, the end cut. And we'll get used to it because it'll come up a lot. Yeah, in the back. In the blue.
We have to add 1.
We still have to add 1. Okay. So, yes, I do want to find the longest walk from W, but I also get 1 point for taking the edge to get there. Okay? Yeah?
Maybe we could save some runtime through catching. For example, in this graph, the two starting node goes into the same node. So that means like they have common paths.
Perfect. So, I imagine trying to compute this for all the vertices and stuff like that. And if I start here, right, it's going to do this recursive call, and it'll do this recursive call. And then on this problem, I'll also do this recursive call again. So we'll see that we're kind of finding ourselves solving the same problem over and over again. Right? So we should save our answers. Okay. So we'll also add some caching. Some dynamic programming on top. And never compute the same LW of V twice. Okay. All right, the algorithm makes sense? At some levels, it's pretty simple algorithm. Okay, so there then is our recursion. And now here comes the running time. Now, again, sometimes we can do the whole thing where we just sum up over subproblems the maximum size of a subproblem. Here I'm suggesting right away that we can do a little bit better than the upper bound. So assuming I'm doing caching, so I'm individually summing up the running time for each problem. Okay, I'm summing over the vertices V, the time it takes to compute LW of V, excluding the recursive subcalls. Okay? And how long roughly would this take? Yeah.
With caching O of M for every edge.
Okay. Sorry?
O of M.
Overall?
Yeah, with caching.
That's right. Okay. So why? So the suggestion is that this is going to be very fast, but why? So for every problem V, say this is V, right? I'm looping over all the edges that leave it. plus maybe a little constant work. So 1 plus the out degree of V. Out degree being the number of vertices going out of V. Okay? So not to introduce more notation, but sometimes this is written as degree plus V. Again, the plus indicates leaving V. Okay? And then if I sum up all the out degrees over all the vertices, each edge gets counted once. Okay? So the whole algorithm comes out as m plus n time. M being the number of edges and n being the number of vertices. Which is obviously quite fast. Okay. Now, going back to a comment from earlier, you could on one hand just set up the caching and then call it recursively and it'll fill out the table. Yeah?
You said the degree of V is just the number of vertices connected to V, right? Like directly? Or...
Yes, which is the number of edges also leaving V. But in particular, I'm looking at the number of edges leaving V, as opposed to the sum of going in and going out, although that would only double the count anyway. Okay. One comment about running this algorithm, you could just set up the recursive algorithm and a caching on top to fill out the table. Or if you wanted, you could topologically order everything ahead of time and then go in order. You'll basically end up doing the same thing. Okay. I guess go in reverse order, but anyway. Okay. All right, so much for that problem. Any questions? Okay. All right, so that addresses the first setting. That turned out to be not only polynomial time, but it took linear time. Which is about as good as I can expect. Okay. Now we'll move on to the general case in general graphs. And if I can just remind myself. Okay, so we thought, most people thought this was hard, and more people abstained on this as well. Okay, very few people thought this was going to turn out to be easy. Does anyone want to change their answer after finding out that you could do it in DAGs in linear time? No? Okay, fine. Okay, so, all right, so now we're working again in regular old-fashioned directed graphs. There may be cycles. Amazingly, this one has one of length 10. And actually what we're going to do is we're going to focus in particular on that special case of trying to figure out if a graph has a path that visits everyone. I'm going to focus on the Hamiltonian path case. Okay? And so this one is going to turn out to be hard. Okay? So we're going to show that a polynomial time algorithm for deciding if there is a Hamiltonian path will allow you to solve stat problems. Okay? All right, so what do we need to do at a high level? We start with some formula, say in CNF. That makes it easier. And somehow we need to turn this into a graph because our black box only takes graphs as inputs. And our black box says yes or no, it has a Hamiltonian path. Okay, so again, sort of like a week ago when we studied independent set, we have to think about how to encode kind of Boolean logic in terms of sort of this logic of paths and graphs. Okay. All right, so here maybe as a starting point for trying to figure out how to do this. So we have a Boolean formula, right? And at some level, we're trying to decide for each xi if it should be true or false. right? Each variable will have some kind of binary decision. So the question is, how do I even try to model xi being true or xi being false, this decision in terms of graphs and paths and graphs? I'm not sure if this is a reasonable question to ask, but I thought I would ask anyway. Are there any suggestions at some level to try to,
whether or not that vertex is part of the Hamiltonian path. So if it is, it's 1, and if it's not, it's 0.
Okay, so that is a good idea, actually. Whether or not it is in the Hamiltonian path could be true or false. So you're thinking a vertex for every variable. And if I visit the vertex, then that should mean, say, you set it to true. And if you don't visit, that means you set it to false. That said, so one thing that's a little bit different is that we're now, that especially makes clear sense with the longest path that we just discussed. But for Hamiltonian path, it's just yes or no, is there a path that visits everyone? So in principle, you want to visit all the vertices, and you just kind of get this all or nothing kind of thing. So there's not as much choice about whether to visit a vertex or not. That makes sense. I think possibly if we had been discussing longest path, that might have led somewhere. It's a good idea, though. Any other? Sure, in the back.
You could just use the adjacency matrix.
Okay, so I give you the adjacency matrix. Yeah? Okay. Well, so it's not just an issue of kind of representing the graph at some level, going from represent an adjacency matrix back to adjacency list and that kind of thing. It all takes polynomial time. That won't really. Yeah.
And I have an idea, but it takes too long, is you can make a bunch of different graphs where each of the xi's is like either in the graph or not, corresponding to 0 and 1, and the one that has a Hamiltonian path is the satisfiable one.
Oh, so for every possible assignment, somehow produce a graph?
Yeah, but that.
Okay. But we're still stuck in kind of effectively brute force land, yeah?
You could turn into 3-sat instead of sat and use the triangle thing.
Oh, okay, we can try to do 3-sat. If I knew that they were only 3 variables, some kind of triangle thing.
Yeah.
That's reasonable. So I guess each vertex will correspond to setting x2 equal to true or something. Okay. Okay, so that's kind of works, except that now I'll suggest that, well, maybe one difference between the style of independent set last week and here is that we kind of, last week we were just like, oh, if you get at least one of these vertices, you're happy, which is like you set one of the assignments to make the class happy. But in sort of a Hamiltonian path still has this feeling of you got to visit everyone. So, any Hamiltonian path will go through all 3 of them anyway. So it still feels a little off between kind of choosing one or the other versus all or nothing. Okay, yeah, one more suggestion.
What if instead of making the vertices the input variables to the Boolean expression, you make the edges those, such that like the combination of edges that is the makes a Hamiltonian path results in satisfying the Boolean expression.
Okay, so one idea is, last time we did model kind of the assignments by vertices, but maybe this time we can model decisions and think about edges instead. Why? Well, here's maybe sort of a kernel of an idea. So here's some vertex that sort of at some level is helping me understand what to do with some variable x2 or something. And maybe I could think of having 2 edges that go into x2. I know I have to visit x2. And maybe taking this edge sort of signifies taking true. And taking that edge signifies taking false. Okay, and then somehow this goes on to do other things. Okay, so the Hamiltonian path, is winding around and has to come through one of the two edges to visit x2. And maybe based on how it enters x2, we can try to read off true or false. Yeah?
What if the desired path actually ended up back to x2, so that both paths into x2 will be used?
Well, I guess if we push this all the way through, what if the Hamiltonian path, what if there's Hamiltonian paths that could use either or something? The different I guess that would mean that there's ways to solve the SAT formula setting x2 equal to true or x2 equal to false, if the whole construction was perfect. Of course, we haven't done much. Yeah?
So, extending onto that idea where you have one edge pointing to x2 and another one, and one is true and one is false, you could make like such a constraint that like if both of the edges are pointing to x2, then the entire satisfiability problem would be false. But if only one was, it would be true, and you do that for like each vertice, and you kind of make like a Boolean expression on that, right? So that only one edge can point to any single vertice, right? Because that's part of the Hamiltonian.
Well, so you draw the edges first. We'll prepare a graph. Then we'll see if there's a Hamiltonian path. The Hamiltonian path, if it existed, would have to take exactly one of these edges, because it can only visit x1 once, from which you should be able to read off true or false. Okay. So here we're gonna do something very much like this, but a little bit more elaborate. Okay. Is that for each variable, I'm going to make a long path with edges in both directions. Okay, a long bidirected path. Okay. Why? Because at some level, imagine that's sort of like the whole graph where it's kind of more or less on an island. If I want to visit all the vertices on this path, I can go in one direction or I can go in the other direction. I can't go both because I would be revisiting vertices. Okay, so any Hamiltonian path that kind of manages to visit all these vertices along the way will have to commit to going one way or the other. Okay. Why a long path and not just one vertex? It'll be useful in a moment. Okay. All right, so we can connect a path for every variable. Okay, sort of in this ladder-like construction. So I have the x1 rung of the ladder, and then the x2 and the x3 and x4. They're all bidirected paths. And sort of when I go from left to right on x1 or something, I now have a choice of going to opposite ends of the next path. Okay, so you kind of imagine going down through the ladder, zigzagging. Each time you get to choose which direction, which should map to some kind of true or false. We haven't done any clauses yet. Okay. All right, so that's sort of the framework for this first preliminary question. Okay, so now, so good. So that's this sort of high-level ladder-style construction. Now, the next part is to figure out what to do about these clauses. Okay. So take, for example, a clause like x1 or not x2. Okay. And, at a high level, we are trying to set up a graph where you can satisfy all the clauses if and only if there's a Hamiltonian path. Okay. So take this clause specifically as an example because it's simple. How might I try to rig? I'll copy it and bring it up above. How can I somehow create some kind of gimmick where, again, following this logic of left or right is true or false? Yeah, at some level, try to encode this into the Hamiltonian path problem. Yeah.
Maybe you could set one of the sides of x1 to be true and the other to be false. And then if it takes the true side, or like if it takes the true direction,
Okay.
when it comes out of that edge, it has to take the
Okay, but that is taking a slight advantage. So okay, so the idea was you want to replace these light blue lines to some extent, to get rid of the crisscross, and somehow encode the fact that you can only get from the x1 ladder to the x2 ladder if you satisfy that clause along the way. Okay? But the only thing I'll suggest is that what if it was x1 or not x3? What if there was both or something? It'll start getting a little messy. That is a good idea, but it does take a little too much advantage of the fact that it's one after the other. I mean, the consecutive part, which is not true in general. There could also be 3 variables in a clause. Here I only put 2, for example, and it's hard to extend that idea to 3. Yeah.
If the dots on the left side, if the path crosses through those, it's true, and if it passes through them first for each clause, then it's true, and then the dots on the right side, if it passes through that one first, then it's false, and then as you move from x1 to x5, you have to make sure that you're on the corresponding.
Yeah. Okay. So let's establish for the rest of, insofar as we're working with this construction, going from right to left should mean true, and going from left to right should mean false, right? So you know that on x1 you have to go. If you're setting x1 to be true, you should be going from right to left. Okay. And somehow you should be able to do something good if you go in that direction but not the other direction. It's too abstract. Okay, so here's what we'll do. So again, let's focus on these 2 rungs. Okay. And what we're going to do is we're going to make a new vertex. Okay, so did I switch this? Okay, that's unfortunate. Let me, all right. X1 or not x2. This one means x1 is equal to 1. Okay. Not sure how that happened. Okay, so again, if I'm going from right to left, that's supposed to signify it being true. And if I'm going left to right, that's supposed to signify it being false. So what we can do is we can make a new vertex represented by maroon. Okay. And if I add directed edges like this, okay, then going right to left, I can detour and visit that vertex. Going left to right, I can't. Okay. And then down here, we can do the same thing. So if I'm going the direction that sets x2 to be false, I can do a quick detour and visit that vertex. That vertex that's just for that kind of associated with that clause. Okay, so these detours are easy and free if you're going in the right direction. If you're going in the wrong direction, like you're going, this way, okay, you can start doing messy things like this. But that could be bad. Maybe now it's impossible to ever visit this vertex. So on and so forth. Okay, we'll figure out how to kind of pad it and adjust things so that you can't cheat like this. All right, so that's the high-level idea. We'll make an extra vertex for every clause. That's very easy to visit if you're going in the correct direction for one of the corresponding variables, and essentially impossible if you're not. Okay. So if you put the whole thing together, it might look like this or something like that. Okay, so we'll have to make the paths wide enough to accommodate all of the vertices. Somehow you don't have to make them that long because you already know that 3 occurrence SAT is also hard. So you can assume, for example, that each vertex only appears in 3 clauses, in which case the paths only have to be constant size or something. Okay. All right, so does the high-level construction make sense? Okay, so it's all set up so that in order to visit all the vertices, you kind of have to weave through the whole ladder, visiting some of these clauses along the way. Okay? And you can only kind of do those detours if you're going in the correct direction. Okay? If I make sure that I kind of leave a little padding in between the purple lines, extra vertices in the middle, that makes it impossible to cheat. I can't like jump into a clause, jump out onto another variable, and find my way back. Okay, so that's the whole proof. Okay, so we can create this kind of ladder-like construction where the rungs represent decisions for each variable. And you can visit some clauses along the way. So spider webs. Okay. How big are these? How big is this graph? Okay, of course it looks a little messy, and I didn't draw the whole thing, but how long does a path need to be? I don't know, roughly the total number of clauses, because it needs to accommodate all the clauses. How many paths there are? There's n. And each clause is adding, at most n more edges. So the total graph, however messy, is still a polynomial size. Okay. So ultimately, we can conclude that if I had a polynomial time algorithm for finding a Hamiltonian path, then I can decide if the SAT formula is satisfiable. Okay. All right, sound good. Any questions? Yeah.
So basically the general idea is like you're starting at like the top, like with x1 of that graph, and then you just have to find a path to the bottom somehow.
Yeah.
Okay.
You have to find a path to the bottom, visiting everyone along the way, which forces you to commit to a direction for each rung. Yeah.
You're visiting every node, even in the ladder graph?
Yes.
Okay.
Because a Hamiltonian path, that's the definition of Hamiltonian path,
Okay.
has to visit everyone. And having all those nodes in the middle forces us to go left to right or right to left. Okay. So what we found then is that there's, for the first time, there's a very sharp contrast between this simple to define problem between DAGs, which allow for recursive enumeration efficiently, and general graphs, where the problem turns out to be very expressive. Okay. All right, so for the remaining time, I've prepared a third problem that's sort of, I thought interesting, because one is a slight preparation for the next lecture, but two, it's sort of, I was hoping to kind of put it in between, conceptually, the two problems we just discussed, or the two settings. Okay, so let me explain. Okay, that was exciting. Okay, so I want to, next time we'll talk about shortest paths exclusively. So this problem is a little bit more artificial. It's trying to find the shortest walk from one point to another, using at most a limited number of edges. Okay, so what does shortest mean if there's already a limit on the number of edges? I'm going to annotate each edge with some kind of length. In this example, I've let them be positive or negative or 0. No constraints. Okay. And sort of the length of a walk will be the sum of those labels over the walk. Okay, so since some labels are bigger than others, it may be advantageous to actually use more edges but those edges individually cost less. And let's say k is at most n or something. K is a modest number. Does the question make sense? I could have just as well asked the longest walk with at most k edges. I chose shortest because next time we'll do shortest path. Okay. So as usual, I've set up one of these votes. Does the question make sense, first of all? Okay. Oh, maybe we should do the example, actually. Okay, so I guess I don't, again, know the answer. I just put the numbers on, and you guys are a black box. So if I said you're allowed to use 8 edges to get from S at the top to T in the bottom right, what is the kind of minimum sum of purple numbers using at most 8 edges? All right, what's your, yeah?
Could you start from S, go to the right,
Okay.
and then go down and to the right, and then go down, and that would be, I think, a sum of 0, and would be 3 edges.
Okay, that's 0, and it fits the constraint. Can anyone do better than 0? Yeah.
I think because the far left, or the cycle on the far left closest to green is negative. You can take that cycle
Okay.
as many times as you want.
All right, help me out. So there's
it's not a cycle anymore, my bad.
Oh, this thing here?
Yeah.
Yeah, the arrows don't quite work. Yeah. So negative cycle, you might hope to spin around and keep driving the score down, although you are still ultimately limited by using 8 edges. Yeah? Yeah.
Can you start on like kind of the middle left?
Oh, so you have to start at S.
Oh, yeah, never mind.
I could have changed the problem where there was no S, but yeah, here in this particular version, you start at S. All right, so the best is 0. Okay, this was not that exciting of an answer compared to last time, but all right, let's say that's the answer. I don't know. Okay, so fine. I've set up a vote. Who's not going to vote? Oh, the question, as usual, is the problem going to turn out to be hard or easy or both? So we got like 5 people not voting. Who thinks it'll be easy? We'll have a polynomial time algorithm. Okay, let's say like 60%. And who thinks it'll turn out to be hard? Okay. Maybe 20%. Okay, I think this is the most closest to parity among the 3 problems so far. Okay. All right. So I don't know what's coming next. Okay. So we are going to come up with an algorithm. Does anyone, before I unveil too much, does anyone want to suggest some approaches? Yeah. Greedy. So if I started at S, what would a greedy algorithm look like?
First choice would probably be take 2.
2. But why not 1?
Yeah, and then take 1.
Okay. Okay, so by greedy, I think you're suggesting the minimum weight outgoing edge. Okay, so if I followed your strategy, see how it does. Maybe I should use a different color. I use green for greedy. Okay, I guess this only has 1 outgoing edge. This has, I have an unlabeled edge. Interesting. Okay, I'll call this 0. Okay. I'm still following greedy, so I would go this way. And, okay, unlabeled edges are just deemed 0. We'll go this way, and we'll go this way. All right. So how did we do? We got 5 minus 3 is 2, plus 1 is 3, 0 minus 1, 2. That's actually not bad. We got 2. But how many edges did we use? Oh, we only used 6. Okay, two things stick out. One is that we didn't do as good as the, of course, optimum solution. And 2, although we got lucky, we weren't keeping track of the number of edges we used. As some of that doesn't factor anywhere into the algorithm, so that's also a concern. Okay. Other ideas? Algorithmic ideas? Yeah.
Similar, we can use a Green algorithm like Dijkstra, and so because I think the trick here is like the uppercase is capped, so we are only going through k most edges. That ensures even if we are doing some sort of breadth first search that goes through all the edges, it doesn't matter because our upper limit is capped, so it should be polynomial.
Okay, so I heard two things in particular. One was the mention of Dijkstra and trying to compute shortest paths. Okay, and probably in the back of your mind, you're thinking, what about negative edges at some level? But then you say, oh, K should put a cap on it. K should help prevent these negative cycles. Okay, I agree. All these statements are true. That said, I'll suggest a couple things. One is, even without negative cycles, Dijkstra can still make mistakes with negative edges. Okay, because Dijkstra is going to keep, we'll talk about next time, is going to keep adding the next closest vertex. But what is the next closest vertex can get revised if you add some negative edges and you find better paths to vertices you've already visited. So even without worrying about negative cycles, that can happen. The next issue is K should help us, right? However, if I use Dijkstra as a black box, we haven't encoded, it's not, K should help us, but we haven't used it at some level, right? And so that's also an issue. Okay. And if we start opening up Dijkstra, then we have to start proving things all over again. Okay. Yeah?
You can use depth first search and track how long the path has been so far. So you have a base case that says, oh, you've made it to day.
Okay, can we build off depth first search? Okay, so one of my concerns is that depth first search will take some path to visit a vertex and mark it off. And suppose that wasn't the best way to even get there. You used up, say, 7 out of 8 edges, and you've already marked it off. And then there was a way to use 2 edges, but you hadn't found it yet. Then, but you've already marked it, so you never get to kind of revise your thinking. And if we start messing with the marking system, it's not necessarily DFS anymore. Yeah?
Could we use a Dijkstra-like algorithm where we keep track of the shortest path to a given vertex and less than or equal to L steps?
Okay, so Dijkstra-like, but at some level, you say, okay, let's replace K with a generic variable L and try to solve various values of L. At some level, you're suggesting almost like an inductive approach. Can we do 1? Can we do 2? Can we do 3? And try to work our way up to K or something. So I don't know if it's Dijkstra-like, but we can take a recursive approach that's also going to maybe keep track of how many edges we've used so far. Okay. All right, so I've already set up, I guess I've suggested a recursion here where I just sort of stated the problem we wanted but replaced sort of the extraneous parameters with variables. Okay, so I wrote SW for shortest walk. This will be the length of the shortest walk from V is one of the input parameters, to T. We'll use the same destination using at most I edges. That's one way to try to break down our problem into smaller problems. Okay. Of course, at the end of the day, we want to replace V with S and I with K. That's the answer we're looking for. Okay. All right. Okay, so much for, we're way ahead of schedule. We're going to finish early. Okay, so that say we want to implement that specification recursively. Okay, so I've set up the base cases for us. I guess I said that if I is less than 0, you're trying to use -1 edges, I'll just say, oh, then you did something wrong. That's plus infinity, you lose. Plus infinity will indicate you didn't find a path. Yeah, this is just one of different ways to do the base case. Okay, let's say otherwise you have at least 0 edges to use. If v is t, then that's good. But if v is not t, then you used up all your edges and you didn't get the t, so that, again, I'll give positive infinity. So the interesting case is when I is at least 0. Okay. And either v is not your destination or v is your destination. Okay. So, good. So, I'll now solicit suggestions for how I might implement the inductive step when v is not t. Okay, so we haven't got there yet. I want to know if I can get there in I edges. Yeah?
So for every edge going out of B, you get the minimum of.
Okay, so I heard minimum over every edge going out of V. So I'll use this notation that was introduced earlier. Okay. Oh, mm-hmm.
SW of W and I minus 1.
SW W I minus 1.
Plus the length of the edge.
Okay, I'll write, I'll just write it in English since I didn't give it a variable. Length of the edge, VW. Okay, so I'm at V. I have many choices of where to go next. I don't know which one, so I try them all. If I try a particular W, I get that length from that edge, and then recursively I'll find the optimum way to get from W to T, which may be positive infinity if there's no way to do it. Okay. I want to return the best one. For us, that's the minimum. I want the shortest walk. Okay, I think that's correct. All right, now what if V is the sink? Not the sink, V is the destination. So V is equal to T. I is greater than or equal to 0 and V is equal to T. Yeah.
Return 0?
Return 0 because I'm already there. Okay. Everyone happy with returning 0? Yeah?
You say it's the shortest walk. Can it be when you get to T and I is not, you have still have some I left. You can get out of T and maybe return it back.
So there is a small catch here. Because the edge lengths are negative, and I'm allowed to repeat vertices. Let's say I get to T and I have 5 edges left. It may in fact be profitable to walk around and get back to T. Maybe there's a negative cycle. Maybe I can keep walking and subtract off 10 points. Okay, it's not very natural to think about, but in this problem that's possible. All right, so, and we don't know which, so we'll take the minimum. On one hand, I can just stop because I'm there. Or I can keep going. So I'm enumerating over all the edges that leave T, the length of the edge, from T to W, plus SW. Okay. Now, something odd has happened. Okay, this algorithm in many ways is very similar to, for example, our algorithm for DAGs, where we have subproblems at each vertex. Right? But there we explicitly use the fact that it's a DAG, okay, to argue that you don't have infinite loops. But this is not a DAG. It's a general graph. Okay. So why is this approach sound? Yeah.
You're decrementing I.
Oh, we're decrementing I. Okay, so I is always going down. So we do have a nice clean induction hypothesis. We're doing induction on I, the base case being I is equal to 0. Or negative, I guess, here. Okay. There's another way to look at this. Okay. That may remind you of the American reachability problem from the PSO. Okay. So let's say I have some graph. Right? And I can think of making k copies of the graph. Okay, so I'll make one copy, just the vertices. Something like this. Okay, and let's say there's k layers total. In this picture, k is just 5. Okay. I should have done 4. Okay. This will actually correspond to k equal to 4 because there's going to be 5 layers, but there'll be 4 sets of edges. Okay. And then we'll draw the edges sort of going down layers, which for that picture will look like this or something. Okay. So we end up making, I guess, k minus 1 or so copies, k copies of the vertex set, k minus 1 copies of the edge set, just from all this stuff. Okay. And so this is obviously a DAG, because we're just going down. Okay. And let's say that you start from S, and S is appearing in every copy, and you want to get to T, and there's a copy of T in every copy of your graph. Okay, and you want to use at most, I guess, 4 edges here. So maybe you're going to start from here, and you can exit from any of these layers, right? Because this means you used at most 4 edges. So I'll make a super kind of version of T, where every copy of T goes to my special version of T. So at some level, I'm asking, what's the shortest way of getting from here to here in this DAG? Okay. We actually could have taken our edge lengths, multiplied them all by -1, okay, and used our first algorithm to find the longest path, or walk, from up here down to here, because longest was the negative, will be shortest with the original. Okay. So implicitly, there's something very similar going on. This is another way to do it. Is this really so slow? I don't know. We make k copies of the graph. Before the algorithm was linear time. So running time doing it this way will be k times m plus n. Okay, so I made k copies of everything. All right, so that's another way of looking at this. All right. But now let me revert back to this recursive approach, which is implicitly very similar. Okay, it doesn't actually make the graphs explicitly. It kind of implicitly navigates these layers with the extra index I. V comma I corresponds to V in the ith layer in the other approach. Okay. All right, so here's our, what's the running time? I guess I filled it in already. Okay. If I was calculating the running time of this recursive approach, where we're not explicitly making that extra graph, it'll start looking a lot like how we did longest path at the beginning in DAGs. Okay. Here I'm enumerating over all I'm summing over all the problems which are indexed by vertex and a layer or a budget I. Okay. The time for that subproblem. Okay. And the time for that subproblem is, like before, for a particular v, 1 plus however many edges I'm looping over. Right? And then I have a k on the outside because I'm doing that k times. Okay. That's wrong. Okay. And we sum all that together, and we again get k times m plus n. Okay, so sort of this more kind of a seemingly more economic approach, where I'm not explicitly creating a graph, and I'm just kind of encoding that logic recursively into those functions, actually gets the same running time as this clumsy approach where I rebuild the whole graph and just find the longest path, even though it seems excessive to rebuild the whole graph. We're actually kind of doing the same thing. One is more concrete than the other. Okay. So what is sort of the takeaway? So this problem turned out to be polynomial time and rather fast. But another big takeaway though is sometimes you can take a problem in a general graph and figure out how to turn it into a problem in a DAG if you can find some kind of ordering. Okay? That's sort of implicit whenever you come up with, the extra index I that's going down. Okay, so there's always this strong connection between situations when we can do recursion plus caching and DAGs. At some level, you can always think, even in terms of sequences with edit distance and stuff like that, you could have always thought of each subproblem as a vertex in a DAG of subproblems. Okay, and those directed edges in the DAG are sort of dependencies of the subproblem. But there's always been an ordering for those algorithms to work. There was always kind of no cyclic dependencies in our subproblems. So this sort of abstract DAG of subproblems was always, in particular, a DAG to make these things work. Okay, so just another way of looking at things. That seems to be what differentiates a hard problem from an easy problem in many cases. All right, that's it. I actually finished early, so no complaints there, I'm sure. Thank you.